The object moves through darkness on a path no human calculation placed it on. Designation 3I/Atlas, the third confirmed interstellar visitor to pass through our solar system, follows a hyperbolic trajectory that will never repeat, never return. It comes from somewhere in the direction of the constellation Ursa Major, though its true origin lies far beyond any single pattern of stars visible from Earth. 4.7 astronomical units from the Sun now, close enough that solar radiation begins to matter, far enough that the cold of deep space still dominates its ancient surfaces. The object tumbles slowly, rotating in a manner astronomers describe as complex, not a simple spin but a wobble, a precession, the motion of something shaped irregularly and unbalanced. It measures perhaps 2 kilometers across. Though uncertainty margins remain wide, no spacecraft has approached it. No probe will intercept its path. All knowledge comes from photons reflected sunlight, thermal emission, the faint glow of atoms excited by solar wind. The object is dark, absorbing most of the light that reaches it, reflecting back only a small fraction. Its albedo, the measure of reflectivity, suggests a surface aged by cosmic radiation, darkened by billions of years in interstellar space where no star's warmth has touched it since it was ejected from whatever planetary system gave it birth. Only took 4.5 billion years to pass through our neighbourhood. The irony sits quietly in the data. The Sun, meanwhile, reaches a peak in its 11-year cycle of magnetic activity. Sunspot groups cluster across the visible hemisphere, dark patches where magnetic field lines pierce through the photosphere and suppress convection. The solar magnetic field reverses polarity during these peaks. North becomes south. South becomes north, a planetary scale transformation that happens with clockwork regularity. But not all solar maxima are equal. This one produces flare activity and coronal mass ejections at rates not recorded since solar cycle 23 in the early 2000s, back when satellite networks were younger and fewer instruments watched the sun's moods. The timing is coincidence. 3I/Atlas did not plan its perihelion passage to coincide with solar maximum. The universe does not arrange such meetings. But the object arrives now, in late 2025, when the sun blazes with magnetic energy and the inner solar system fills with charged particles moving at hundreds of kilometers per second. The two ancient wanderer and active star meet in the quiet of space where no sound carries, where distance swallows most of what happens, where only patient telescopes bear witness. Astronomers track 3I/Atlas through networks of instruments spread across Earth's surface and in orbit above the atmosphere. The object appears as a point of light, sometimes steady, sometimes varying. Its brightness changes on timescales of hours and days, fluctuations that might indicate rotation, outgassing, or something else. The light curve, a graph of brightness over time, becomes a text written in photons, a message about composition and behavior that requires interpretation. Early observations show nothing extraordinary. The object behaves as interstellar objects are expected to behave: dark, inert, slowly tumbling through the inner system on its way back to the depths from which it came. Then, on November 3rd, something changes. The brightness increases, not gradually, but within hours, a spike in luminosity that makes 3I/Atlas suddenly brighter by 40%. As if someone turned up a dimmer switch, the change is undeniable. Multiple observatories confirm it independently. Whatever causes this increase leaves no obvious signature in the spectrum, no new emission lines, no change in colour, just more light. The increase happens to coincide with a major coronal mass ejection directed along the ecliptic plane. 1.3 billion tons of plasma, accelerated to 700 kilometers per second, racing outward from a sunspot group designated AR 3889. The ejection is not aimed at Earth. Its trajectory carries it southward of the ecliptic, but it passes near the orbital path of 3I/Atlas. Perhaps near enough. Space is mostly empty, but the solar wind during these events is not a narrow beam but a wave, a pressure front that compresses the ambient solar wind ahead of it and sends magnetic field lines spiralling outward in complex geometries. Only took 93 million miles for the sun's exhalation to reach the object. A day and a half of travel time for particles that could cross Earth's diameter in 2 minutes. The brightening persists for 36 hours, then begins to fade. Not quickly, but gradually, as if whatever process began is now winding down. Brightness returns to near baseline levels, though not exactly baseline. A residual glow remains, subtle but measurable. Observers note it in their logs. Some wonder if the effect will repeat. Some begin checking solar activity forecasts, correlating predicted coronal mass ejections with the object's position. The hypothesis forms quietly among research groups, perhaps 3I/Atlas. Responds to solar wind pressure in ways that produce light. This would not be unprecedented. Comets brighten when solar radiation sublimates their ices. Asteroids can brighten when dust is released from their surfaces. But 3I/Atlas is neither comet nor asteroid in the traditional sense. It is a visitor from another star system, formed under unknown conditions, composed of materials shaped by processes no human has witnessed. Its behavior might follow familiar patterns or might reveal something new. The question sits unanswered in the data, waiting for more observations, more events, more time. The object continues its inward drift. 4.5 astronomical units now, still too far for most volatiles to sublimate vigorously under normal solar conditions. Water ice requires closer approach, warmer temperatures, before it begins to stream away as vapor. Carbon dioxide sublimates more easily, but even CO2 ice should remain stable at these distances under typical solar irradiance. The mystery is not that 3I/Atlas can brighten many objects do, but that it brightens here, now, when solar heating alone seems insufficient, unless the solar wind provides not just pressure but energy, unless magnetic fields embedded in the plasma interact with materials on the object's surface, unless decades of interstellar travel left the surface in a state more fragile than expected, primed to respond to even modest disturbances. The possibilities multiply quietly in research papers yet to be written. Night falls across observatory sites as Earth rotates. The object remains visible in southern hemisphere skies, tracked by robotic telescopes that neither sleep nor blink. Data accumulates in digital archives. Light curves extend rightward across time axes, and somewhere in the flow of photons and timestamps, the story of 3I/Atlas continues to write itself in the only language it knows. The sun does not care about observers. It burns hydrogen into helium in a core where temperatures reach 15 million degrees Celsius, where pressures would crush any material humans know into plasma. The energy generated there takes 170,000 years to random walk outward through the radiative zone, buffeted by countless absorptions and re-emissions, before reaching the convective zone where rising and falling plasma cells carry heat to the surface. What emerges as light left the core during the Holocene's beginning, when Earth's climate was stabilizing after the last ice age, when humans were just learning to farm wheat in the Fertile Crescent. But the sun's magnetic field operates on faster timescales. 11 years, roughly, sometimes 9, sometimes 13, but averaging to 11 with remarkable consistency over the 4 centuries humans have been counting sunspots. The field originates from the differential rotation of the sun's interior. The equator spins faster than the poles, stretching and twisting magnetic field lines like rubber bands wound too tight. Eventually, the field becomes so tangled, so stressed, that it breaks through the surface in loops and arcs, creating active regions where sunspots form and flares erupt. The current cycle, solar cycle 25, began in December 2019. The transition was subtle. For months, few sunspots appeared. The sun's face looked clean, quiet, almost blank. Scientists tracking the cycle waited for the characteristic pattern's new spots appearing at higher latitudes, with magnetic polarities reversed from the previous cycle. When those signs emerged, they confirmed that cycle 24 had ended and cycle 25 had begun. Predictions varied. Some models forecast a weak cycle, similar to the subdued activity of cycle 24. Others suggested moderate strength. None predicted what actually unfolds now, a solar maximum that rivals the most intense peaks in recorded history. Only took 6 years for the sun to ramp up to this. Faster than expected, stronger than models suggested. By November 2025, the sun's visible hemisphere hosts 17 major sunspot groups simultaneously. Some span diameters larger than Jupiter. The largest, AR 3,891, stretches across 200,000 kilometers, a magnetic complexity classified as beta-gamma delta, the designation reserved for regions capable of producing X-class flares. These regions are not stable. They evolve over days, fragmenting and merging, as magnetic flux emerges from below and interacts with existing fields. Watching the sun during solar maximum is like watching a slow-motion storm system that never resolves, never settles, only transforms from one configuration of chaos to another. The photosphere appears mottled through filtered telescopes. Bright faculae surround the dark umbra of sunspots. Granulation patterns, the cellular structure of convection shift and boil everywhere. Magnetic fields do not suppress them. The chromosphere above glows in hydrogen alpha light, revealing filaments and prominences arcing hundreds of thousands of kilometers into the corona. Some of these prominences are quiescent, held in place by magnetic tension for days or weeks. Others are eruptive, rising and breaking free, contributing mass to coronal mass ejections that race outward into interplanetary space. The corona itself, visible only during eclipses or through specialized coronagraphs, extends in complex streamers and loops that trace magnetic field lines. During solar minimum, the corona appears relatively simple equatorial streamers and open polar field lines. During maximum, the structure becomes chaotic. Closed magnetic loops trap hot plasma near the surface. Open field lines allow solar wind to escape at high speeds. The boundary between closed and open regions shifts constantly. Magnetic reconnection, the process where field lines snap and reconfigure, releases enormous energy in small volumes, heating plasma to millions of degrees and accelerating particles to near relativistic speeds. The solar wind itself is not uniform. It consists of slow wind flowing at 300 to 500 kilometers per second, and fast wind reaching 700 to 800 kilometers per second. The slow wind originates from closed magnetic regions near the equator, where plasma escapes through complex field geometries. The fast wind comes from coronal holes, regions where magnetic field lines open directly into space. During solar maximum, coronal holes shrink and migrate toward the poles, reducing fast wind. But coronal mass ejections more than compensate, injecting massive pulses of plasma that travel faster than either slow or fast wind, creating shock waves that compress and heat the ambient solar wind ahead of them. Only took 8 minutes for the light to reach Earth. The plasma takes days. 3I/Atlas moves through this environment. The object does not experience solar wind as a steady breeze, but as a variable medium with structure, turbulence, and sudden changes. The Parker Solar Probe, humanity's closest emissary to the Sun, has measured these variations at distances far closer than 3I/Atlas currently occupies. The probe's instruments record switchback sudden reversals in magnetic field direction, magnetic islands, flux ropes, and other structures embedded in the solar wind. These features are not rare. They are ubiquitous, filling the inner heliosphere with complexity that earlier models did not predict. The interstellar object encounters this complexity from a perspective no probe will ever share. It approaches from outside the ecliptic plane, crossing through different streams of solar wind than Earth experiences. Its trajectory carries it through regions where fast and slow wind collide, where coronal mass ejections plough into ambient plasma, where the heliospheric current sheet the warped surface separating opposite magnetic polarities undulates like a skirt's hem in 3 dimensions. On November 8th, the Sun produces an X2, 4-flare from AR 3891. The flare's electromagnetic radiation reaches Earth in 8 minutes, causing radio blackouts across the sunlit hemisphere. The associated coronal mass ejection launches an hour later, observed in coronagraph images as a bright halo expanding outward. Initial trajectory analysis suggests the ejection is not Earth-directed, but moves southward, toward the region of space where 3I/Atlas currently resides. The ejection carries a magnetic field structure known as a magnetic cloud, a coherent, rotating field geometry embedded in the plasma. Such structures are dangerous to spacecraft electronics when they strike Earth. They're also extremely effective at compressing and heating ambient material. When a magnetic cloud encounters an object in space, the interaction depends on whether the object has its own magnetic field. Earth's magnetosphere deflects and channels solar wind around the planet. Objects without magnetic fields, like most asteroids and comets, experience the solar wind directly, absorbed into their surfaces or deflected around them. Whether 3I/Atlas has a magnetic field remains unknown. The object is too distant, too small, for magnetometers to detect any field it might possess. If it formed from a differentiated parent body, perhaps it retains remnant magnetization in metal-rich regions. If it is merely a fragment of undifferentiated rubble, likely it carries no organized field. The question is one more item on a long list of unknowns. The coronal mass ejection travels outward at 900 kilometers per second, faster than the November 3rd event. More massive, the shockwave ahead of it accelerates particles to high energies, creating what space physicists call solar energetic particle events. These particles, mostly protons, with smaller populations of helium nuclei and electrons, spiral along magnetic field lines, sometimes reaching speeds approaching half the speed of light. They arrive at Earth before the bulk plasma, detected by satellite instruments as sudden increases in radiation levels. Only took 49 hours for the bulk of the ejection to reach 3I/Atlas's position. The energetic particles arrived sooner. Observatories continue monitoring. Telescopes in Chile, Hawaii, and South Africa track the object's brightness. Some observers use broadband filters, measuring all visible light together. Others employ narrowband filters, isolating specific wavelengths hydrogen alpha, oxygen emission lines, sodium D lines. Each wavelength tells a different story about what processes might be active on the object's surface or in any tenuous atmosphere it develops. The Sun rotates with a period of about 25 days at its equator, 35 days near its poles. Active regions carried by this rotation move across the visible disk, disappearing over the western limb and emerging 2 weeks later on the eastern limb if they survive that long. Many regions decay within a week. Some persist for months, surviving multiple rotations. AR 3891, the source of the X2. 4-flare, rotates toward the western limb now, its most geo-effective position behind it, but other regions emerge to replace it. The Sun during maximum is never quiet for long. The magnetic field embedded in the solar wind points in different directions depending on which hemisphere of the Sun it originated from. Field lines in the northern hemisphere point away from the Sun or toward it. Depending on the cycle phase, field lines in the southern hemisphere point in the opposite direction. The boundary between these regions, the heliospheric current sheet, divides the heliosphere into sectors of opposite polarity. Crossing this boundary means encountering a sudden reversal in magnetic field direction, which can affect how charged particles behave and how structures in the solar wind evolve. 3I/Atlas crosses through different sectors as it moves along its trajectory. Each crossing exposes it to different magnetic conditions, different particle populations, different pressures. The object does not record these crossings in any way humans can access later. It simply experiences them, absorbs them, responds to them in whatever manner its composition and structure allow. The result is brightness changes, subtle shifts in reflected light, variations that telescope observers dutifully record without yet understanding their cause. Plasma is matter stripped to its essentials, electrons torn from atoms, leaving positively charged ions and free negative charges that move independently. It is the fourth state of matter, though in the universe's accounting it is the first state, the most common, the most widespread. 99% of visible matter exists as plasma. Stars burn in it. Nebulae glow with it. The space between worlds fills with it, thin beyond measure but present nonetheless. The coronal mass ejection from November 8th consists of approximately 2 billion tons of plasma, mostly hydrogen ions, protons, with some helium nuclei and trace amounts of heavier elements. The mass sounds enormous until scaled against the Sun's total mass, 2 times 10 to the 30th kilograms. The ejection represents 1/10,000,000th of the Sun's substance, a rounding error, an exhalation that costs the star nothing. Yet this trivial fraction, accelerated to 900 kilometers per second, carries kinetic energy equivalent to hundreds of thousands of nuclear weapons. Not that anyone is counting. Not that the comparison means anything in the vacuum where no shockwave propagates, where destruction requires direct contact. The plasma does not travel as a uniform cloud. It forms a structure. The leading edge is a shock wave, not a sound wave, but a collisionless shock where electromagnetic forces pile up and compress the ambient solar wind. Behind the shock comes the magnetic cloud, a twisted flux rope where field lines wrap around a central axis like strands in a cable. The field strength inside the cloud measures 50 nanotesla, weak by laboratory standards but significant in interplanetary space. The field rotates smoothly as the cloud passes, a signature that identifies these structures in spacecraft data. Only took the shock wave 47 hours to reach 3I/Atlas. The magnetic cloud arrived 6 hours later. The object at this moment occupies a position 4.4 astronomical units from the Sun, roughly the orbital distance of Jupiter. Though 3I/Atlas does not orbit, it passes through. The ambient solar wind here, under normal conditions, flows at 400 kilometers per second with a density of approximately 1 particle per cubic centimeter. 1 particle per cubic centimeter, vacuum by any terrestrial standard, yet still denser than the interstellar medium the object has travelled through for uncounted millennia. When the shock arrives, the solar wind ahead of it does not have time to move out of the way. Instead, it compresses. Density jumps to 5 particles per cubic centimeter. Temperature increases from 50,000 degrees to 500,000 degrees. Magnetic field strength triples. The transition happens across a distance of a few hundred kilometers, effectively instantaneous for an object measuring 2 kilometers across. One moment, 3I/Atlas sits in a normal solar wind. The next moment, it bathes in shocked plasma. The object's surface temperature, prior to the shock's arrival, hovers around 130 Kelvin, cold enough that water ice remains stable indefinitely, cold enough that carbon dioxide ice sublimates so slowly that a layer 1 meter thick would take centuries to erode, cold enough that most volatiles humans are familiar with exist as solid crystals, locked in place by molecular forces. But cold is relative. 130 Kelvin is warmer than most objects ever get in interstellar space, where temperatures approach the cosmic microwave background's 3 Kelvin floor. 3I/Atlas has been warming slowly since it entered the inner solar system, gaining heat from sunlight that, even at this distance, delivers more energy than the frigid depths between stars. The shock's arrival does not immediately raise the surface temperature. Plasma moving at 900 kilometers per second does not collide with the surface like a solid object. Individual particles strike, transferring momentum and energy, but the density remains low enough that most particles miss entirely. A surface area of 1 square meter on 3I/Atlas intercepts approximately 30 million solar wind protons per second under normal conditions. During the shock passage, that number increases to perhaps 150 million per second. Still sparse, still mostly empty space. Yet the cumulative effect matters. Each proton carries kinetic energy. When a proton strikes the surface, it either bounces off, embeds itself, or causes a sputtering event where surface atoms get knocked free. The energy deposited heats the immediate impact site on atomic scales. Most of this heat radiates away almost immediately, but some conducts inward, warming subsurface layers. Over hours, over days, the cumulative heating becomes measurable. Only took a few centimeters of depth for the temperature gradient to flatten. Below that, the interior remains as cold as it has been for geological ages, but something else happens when charged particles strike the surface. They bring magnetic fields with them. The particles gyrate around magnetic field lines, spiraling in helical paths with radii determined by their energy and the field strength. When the magnetic cloud passes over 3I/Atlas, the object finds itself immersed in a 50 nanotesla field rotating slowly through different orientations. If the surface contains any conducting materials, metals, carbon compounds, salts dissolved in ice, then electric currents can be induced by the changing magnetic field. These currents are weak, measured in microamperes per square meter, but they flow nonetheless, and where currents flow, resistive heating occurs. The question is whether 3I/Atlas contains enough conducting material for this to matter. A pure ice ball would respond minimally. An object with metal-rich regions, perhaps fragments from a differentiated parent body's core, might respond more vigorously. The answer is locked inside the object, invisible to remote observation, a parameter that can only be inferred from behavior. Observers in South Africa detect the second brightening event on November 10th at 22:14 UTC. The brightness increases by 70% over baseline within 4 hours, more dramatic than the November 3rd event, more sustained. The increase plateaus for 8 hours, then begins declining. By November 12th, brightness has returned to near baseline, though again a residual glow persists, slightly brighter than before the event. Spectroscopic observations during the brightening reveal sodium D-line emission, 2 narrow lines at 589.0 and 589.6 nanometers, the characteristic signature of neutral sodium atoms excited by sunlight or particle impact. Sodium emission is common in comets. It appears when solar radiation liberates sodium from minerals in dust grains. Sodium atoms. Once free, scatter sunlight efficiently. A small amount of sodium produces visible emission. The detection suggests that 3I/Atlas is releasing dust or vapor, that something on its surface or just beneath is being disturbed enough to free atoms into the surrounding space. Other emission lines remain absent or below detection limits. No strong oxygen lines. No obvious water vapor signatures. No cyanogen or carbon monoxide bands. Either these species are not present in significant quantities, or they are not being released at rates sufficient for detection. The sodium emission stands alone, a single clear signal in a spectrum otherwise dominated by reflected sunlight. The mystery is not that sodium exists. Sodium is common in solar system materials. The mystery is why it appears now, during solar wind events, rather than continuously as the object warms from solar heating. Why the correlation between coronal mass ejections and brightness changes. Why the lag time between shock arrival and peak brightness matches the timescale for surface heating, rather than immediate response. Only took a few hours for human observers to notice. The process itself took longer to unfold. Some researchers propose that 3A/Atlas has a layered structure, perhaps a surface of refractory material, darkened by radiation damage, covering more volatile rich layers beneath. The solar wind shocks, they argue, provide enough energy to breach this outer layer in localized regions, exposing subsurface ices to sunlight and causing outgassing. The outgassing lofts dust particles that reflect sunlight, increasing brightness. Sodium atoms liberated from the dust produce the emission lines. Others suggest the object might be fragmenting. Thermal stress from solar heating combined with mechanical stress from impacts and tidal forces could crack the structure. Cracks expose fresh surfaces. Fresh surfaces contain volatiles that immediately sublimate. The fragmentation hypothesis is harder to test without high-resolution imagery showing changes in the object's shape. No such imagery exists. 3I/Atlas remains a point source, its structure unresolved. A third hypothesis proposes that 3I/Atlas contains subsurface voids or porous regions where volatiles have accumulated. Heating from solar wind impacts warms these regions, increasing sublimation rates inside the voids. Pressure builds until gas escapes through cracks or weak spots, carrying dust with it. This model explains the delayed response and the correlation with solar wind events, but it requires assumptions about internal structure that cannot be verified. The truth is likely some combination, or something else entirely. Space is filled with objects that do not behave exactly as models predict, that reveal complexity when examined closely, that remind scientists how much remains unknown about even familiar classes of bodies. An interstellar visitor amplifies this uncertainty. It formed elsewhere, under conditions perhaps different from solar system norms, from materials that might include compounds rare or absent in local space. The magnetic cloud passes, the field strength decreases, the plasma density returns to background levels. The shock wave, having compressed the ambient solar wind, continues outward, expanding and weakening, becoming one more disturbance in the heliosphere's chaotic medium. Behind it, 3I/Atlas continues its inward journey, now visibly changed brighter than before, emitting sodium, carrying evidence of processes that remain incompletely understood. Ice does not melt in vacuum. There is no liquid phase transition when pressure drops below 611 pascals, the triple point of water. Below that threshold, ice sublimates directly to vapor, molecules breaking free from crystal lattice bonds and escaping into space. The process is quiet. No boiling, no bubbling, no surface turbulence. Individual molecules gain enough thermal energy to overcome binding forces, then simply leave. The rate depends on temperature and the binding energy of the particular ice structure. Water ice exists in at least 18 crystalline forms, each stable under different pressure and temperature conditions. Ice IH hexagonal ice. The form familiar from Earth's winter is what forms on Comet surfaces and presumably on 3I/Atlas if water ice is present. Its sublimation rate at 130 Kelvin is approximately 10 to the minus 12 kilograms per square meter per second, extraordinarily slow. A surface layer 1 meter thick would take 30 million years to sublimate completely at that temperature. This is why comets from the Oort cloud can survive for billions of years in cold storage, why objects in the Kuiper belt retain their volatiles, why 3I/Atlas could travel through interstellar space for geological ages without losing all its ices. But temperature increases change everything. Sublimation rate depends exponentially on temperature. At 150 Kelvin, the rate increases by 2 orders of magnitude. At 170 Kelvin, another factor of 10. By 200 Kelvin, water ice sublimates vigorously enough to produce visible Comet around active comets. The relationship follows the Clausius-Clapeyron equation. a thermodynamic principle governing phase transitions that applies equally to water. Carbon dioxide, methane, ammonia, and other volatile species only took 20 degrees of warming to increase sublimation rate by 100 times. Exponential functions are merciless in their acceleration. 3I/Atlas's surface temperature prior to November 10th averaged 130 Kelvin. After the coronal mass ejection passes, localized regions warm to 160 Kelvin or higher. Not the entire surface, only areas where solar wind particle flux is concentrated, where magnetic field interactions are strongest, where surface composition allows heat absorption. These hot spots, perhaps dozens of them scattered across the object's rotating surface, become sites of enhanced sublimation. The sublimating ice creates a thin atmosphere. Calling it an atmosphere is generous. The gas density at the surface reaches perhaps 10 to the 12th molecules per cubic meter, still a hard vacuum by terrestrial standards, but dense enough that molecules collide occasionally, dense enough that the expanding vapor forms a flow rather than individual ballistic trajectories. This is the beginning of a coma, the cloud of gas and dust that surrounds active comets. The atmosphere does not stay. Escape velocity from a 2-kilometer object is roughly 1 meter per second. Water vapor molecules at 160 Kelvin move at approximately 500 meters per second on average. They leave the surface and never return. Some molecules collide with other escaping molecules, exchanging momentum, but the collisions are too infrequent to establish an equilibrium. The atmosphere is transient, existing only as long as sublimation continues, dissipating within hours once the heat source diminishes. Carbon dioxide sublimates more readily than water. CO2 ice has a vapor pressure that becomes significant at temperatures as low as 90 Kelvin. If 3I/Atlas contains carbon dioxide ice, it would sublimate first, possibly carrying water ice grains with it as it escapes. The expanding CO2 gas would drag dust particles and chunks of ice along, lifting them from the surface and lofting them into the surrounding space. This mechanism, the entrainment of dust by sublimating gas, is responsible for most dust emission from comets. Observations show brightness increasing, which requires light scattering material to be present in the surrounding space. That material is dust, individual grains, likely ranging from micrometers to millimeters in size, composed of silicates, organics, possibly metal compounds. The grains were embedded in ice or loosely bonded to the surface. Now they drift outward, propelled by gas pressure and by radiation pressure from sunlight. Each grain scatters sunlight according to its size and composition. Collectively, they increase the cross-sectional area of light-scattering material around 3I/Atlas, making the object appear brighter, even though the solid nucleus itself has not changed. Only took a few million dust grains to create the observed brightness change. Perhaps a few tons of material total, lifted from localized regions no larger than football fields. The sodium emission detected in spectra comes from these dust grains. Sodium is a minor component of most cosmic dust, perhaps a few percent by mass in silicate grains, higher in some mineral types. When dust grains are exposed to sunlight in space, photons can liberate sodium atoms from the grain surfaces through photodesorption. The sodium atoms, once free, absorb sunlight at specific wavelengths and re-emit it as fluorescence. The process is efficient. A single sodium atom can scatter hundreds of photons per second in bright sunlight. Even small amounts of sodium produce detectable emission. The sodium emission reveals something about the dust composition. The grains likely contain sodium-bearing minerals, possibly feldspars, pyroxenes, or clay-like phyllosilicates. These minerals are common in solar system asteroids and meteorites. Their presence in 3I/Atlas suggests that whatever planetary system the object formed in had similar chemistry to our own: silicon, oxygen, aluminum, sodium, magnesium. The same elements dominate rocky materials everywhere because these elements are abundant products of stellar nucleosynthesis. Different stars produce different element ratios, but the basics remain consistent. The dust particles do not remain near 3I/Atlas. Solar radiation pressure pushes them outward, away from the Sun. The force is weak a few piconewtons per grain, but over days and weeks. It accelerates the grains to speeds of tens of meters per second. Larger grains, with more mass, accelerate more slowly. Smaller grains, with less mass, accelerate faster. The result is a spreading cloud of dust, sorted by size, with the smallest grains forming a tail that points directly away from the Sun. This is not yet a visible tail. The dust density is too low, the tail too faint, the object too distant for most telescopes to resolve extended structure. But spectral observations hint at asymmetry. The sodium emission appears slightly elongated in one direction. Image processing techniques that subtract the point spread function of the telescope reveal faint excess light in an anti-sunward direction. The measurements are marginal, close to noise limits, but consistent with early tail formation. The tail is not unique to 3I/Atlas. All active comets develop tails. What makes this tail noteworthy is its origin, an interstellar object responding to solar wind disturbances rather than to steady solar heating. The tail's existence confirms that the brightening is not merely reflected light increasing, but actual mass loss, actual material being expelled from the object. Only took 4.5 billion years in interstellar space before the object decided to shed dust in our solar system. The universe is patient with its ironies. The gas escaping from 3I/Atlas also forms a tail. Though gas and dust tails are distinct, gas molecules being charged or easily ionized by solar ultraviolet light get swept away by the solar wind's magnetic field. The solar wind moves faster than radiation pressure pushes dust, so the gas tail typically points more directly anti-sunward and extends farther. Gas tails glow through fluorescence molecules, absorbing sunlight and re-emitting it at specific wavelengths. The most common emissions in cometary gas tails come from cyanogen, carbon monoxide, water, and hydroxyl radicals. No such emissions appear strongly in 3I/Atlas spectra. Either the gas production rate is too low for detection, or the gas composition is unusual, or the observing geometry makes gas emission difficult to see. The absence is puzzling. Water ice sublimates into water vapor. Water vapor should be detectable if present in sufficient quantity. Its absence suggests either that water is not the primary volatile being released, or that the outgassing rate is lower than expected, or that observational limitations prevent detection. The mystery compounds. Each new observation answers one question and raises 3 more. The object brightens during solar wind events, that much is clear. It releases dust and sodium confirmed. But the full inventory of what escapes from 3I/Atlas, where it comes from, and why it responds so specifically to solar wind shocks rather than continuous solar heating, remains unresolved. Researchers request telescope time to continue monitoring. Proposals are written, submitted, reviewed. Some are approved, others are not. Telescope time is precious, oversubscribed by factors of 3 or 4. Not every interesting object gets the coverage it deserves. 3I/Atlas competes with supernovae, exoplanet transits, galaxy surveys, near-Earth asteroid monitoring. It gets some time. Not as much as a dedicated study would require. Observations continue, but with gaps. Some nights are lost to weather, some to equipment failures, some to higher priority targets that override the schedule. The object does not care about scheduling conflicts. It continues inward, warming slowly, responding to solar wind variations, carrying its secrets without concern for human curiosity. The solar wind is not wind. Wind implies air, atmosphere, convection driven by pressure gradients. The solar wind is an expansion plasma flowing outward because the sun's corona is hot enough that gravity cannot hold it. 2 million degrees Kelvin in the corona, hot enough that hydrogen ions move at hundreds of kilometers per second in thermal motion. Some fraction of those ions have velocities exceeding the sun's escape velocity at that altitude. They leave, they never return. The sun loses approximately 1 billion kilograms of mass per second this way, bleeding plasma into space, a hemorrhage that will continue for billions of years without significantly depleting the sun's total mass. The flow is supersonic, near Earth. The solar wind travels at 400 kilometers per second, while the sound speed in that plasma is only 50 kilometers per second. This means disturbances cannot propagate upstream. Information travels only downstream. Cause and effect flow outward from the sun, never inward. 3I/Atlas experiences the solar wind as a stream, a river of charged particles that carries information about conditions at the sun from days earlier but tells the sun nothing about what happens out here in the current. The wind carries more than particles. It carries magnetic field. The field originates in the sun's interior, emerges through the photosphere in active regions, extends into the corona, and gets dragged outward by the flowing plasma. This is the interplanetary magnetic field, a structure that spirals outward in a pattern called the Parker spiral, named for Eugene Parker, who predicted the solar wind's existence before spacecraft confirmed it. The spiral forms because the sun rotates while the wind flows outward. Field lines anchored to the rotating sun curve backward, like water from a rotating sprinkler, creating a spiral pattern that extends throughout the heliosphere. Only took until 1959 for a human to predict this. The prediction came from equations, not observation pure theory that turned out to be correct. The magnetic field strength at 3I/Atlas's current position averages around 5 nanotesla under quiet conditions. 5 billionths of a Tesla. For comparison, Earth's magnetic field at the surface measures 50,000 nanotesla. A refrigerator magnet produces fields of 10 million nanotesla. The interplanetary magnetic field is weak by everyday standards, but in the context of plasma physics, even weak fields matter. Charged particles gyrate around field lines. Their motion is not free but constrained, spiraling along the field direction while drifting perpendicular to it. The field guides particle flow, channels energy transport, and mediates momentum transfer between the solar wind and any object it encounters. When coronal mass ejections pass, the field strength increases dramatically. The November 10th magnetic cloud carried a 50 nanotesla field 10 times stronger than background. This stronger field compresses, heats, and accelerates plasma more efficiently. It also interacts more strongly with any conducting materials in its path. If 3I/Atlas were a metallic sphere, the passing magnetic field would induce electric currents in the metal through Faraday's law of induction. A changing magnetic field creates an electric field which drives currents in conductors. Those currents generate their own magnetic field, which opposes the change in the external field. This is electromagnetic induction, the principle behind electric generators and transformers, operating here on a planetary scale with a 2-kilometer object as the conductor. But 3I/Atlas is not a metallic sphere. It is likely a rubble pile, an aggregate of smaller pieces loosely bound by gravity and perhaps weak cohesive forces. The object's low density, estimated from brightness variations to be around 1 gram per cubic centimeter, suggests high porosity, perhaps 50% voids by volume. Porous structures do not conduct electricity well unless their matrix material is conductive. Ice is not conductive. Silicate rock is not particularly conductive. But many materials become more conductive when they contain impurities. Salts, or trace metals. The question is whether enough conducting pathways exist within 3I/Atlas to allow significant induced currents, even weak currents, flowing through resistive material. generate heat through Joule heating, the same process that warms the filament in an incandescent bulb. If the object's interior contains even a modest network of conducting grains or veins, the passing magnetic cloud could deposit energy throughout a substantial volume, not just at the surface. Only took a magnetic field 10 times stronger than usual to make this effect potentially significant. Whether it actually matters depends on composition. Calculations suggest that for an object of 3 I/8 size and estimated conductivity, the energy deposited by induced currents during a magnetic cloud passage could heat subsurface layers by several degrees over the course of hours. Not dramatic heating, not enough to melt ice, but enough to increase sublimation rates in volatiles already near their sublimation point, enough to release gas trapped in porous structures, enough to create pressure differentials that drive outgassing. This mechanism would explain the delayed response. Solar wind shocks arrive, magnetic fields intensify, currents are induced, resistive heating accumulates, temperatures rise over hours, sublimation accelerates, gas escapes, dust is lofted, brightness increases. The timeline matches observations. The correlation with magnetic clouds rather than simple shock waves makes sense. Stronger fields induce stronger currents, deposit more energy, produce more heating. The hypothesis is testable. In principle, if electromagnetic induction drives the brightening, then the effect should scale with magnetic field strength. Stronger magnetic clouds should produce brighter outbursts. Weaker shocks with minimal field enhancement should produce little or no brightening. Solar wind streams without magnetic field increases, such as fast wind from coronal holes, should have minimal effect. The pattern should be clear in data once enough events accumulate. Only 3 significant events have occurred so far. Too few for statistical confidence. Too few to establish clear correlations. More data is needed. More solar windstorms. More monitoring. More time. The Sun, fortunately, is cooperating. Solar Cycle 25's maximum phase is expected to continue through 2026. During that time, dozens of coronal mass ejections will occur. Not all will reach 3 I/8's position. Not all will have the right geometry, but some will. Each event provides another data point, another opportunity to test hypotheses, another chance to learn what this object is made of and how it responds to disturbances. The object's rotation complicates interpretation. 3 I/Atlas rotates with a period of approximately 7.3 hours, based on periodic brightness variations observed before the outgassing began. The rotation means that different parts of the surface face the Sun and the incoming solar wind at different times. If outgassing is localized to specific regions, perhaps areas with thinner surface layers or unusual composition, then the brightness should vary not only with solar wind conditions but also with rotation phase. Early data hints at this. The November 10th brightening event shows substructure smaller peaks and valleys in the light curve occurring on timescales of a few hours, consistent with rotation. Perhaps active regions rotate into and out of view. Perhaps different regions respond differently to heating. Perhaps the object's shape is irregular enough that solar illumination varies significantly as it tumbles. The rotation itself is complex. Initial observations suggested simple rotation, but more detailed analysis reveals precession. The rotation axis wobbles over longer timescales. This is common for irregularly shaped objects. Angular momentum conservation requires that total spin remains constant, but the axis around which the object rotates can shift if the object is not a perfect sphere. The precession period for 3 I/Atlas appears to be roughly 30 days, though uncertainty remains high. Only took careful photometry over weeks to detect this. The precision required is remarkable brightness changes of 1 or 2%, measured from millions of kilometers away. Precession affects which parts of the surface receive solar heating and solar wind exposure over time. Regions near the rotation poles experience different conditions than equatorial regions. if the poles are capped with more volatile rich ice, as happens on some comets, then precession could periodically expose these caps to enhanced solar wind flux, triggering outbursts that correlate not only with solar activity, but also with the object's orientation. This adds another layer of complexity to an already complex system. Solar wind variability, surface heterogeneity, rotation and precession, composition uncertainties. Each factor influences the others. Predicting brightness becomes an exercise in multivariate modelling with poorly constrained parameters. Researchers do their best. Models are built, parameters adjusted to fit observations, predictions made. Some predictions succeed, others fail, the models improve incrementally. Science proceeds this way: observation, hypothesis, prediction, testing, refinement. The process is slow. It requires patience, careful work, skepticism of easy answers. 3I/Atlas does not make it easy. The object reveals itself reluctantly, in fragments, through indirect signals that require interpretation. But this is how knowledge accumulates. This is how understanding grows, piece by piece, data point by data point, over months and years of persistent effort. Comets have tails. This has been known for thousands of years. Ancient Chinese astronomers recorded comets as broom stars. Greek philosophers debated their nature. Medieval Europeans saw them as omens. Not until the 17th century did astronomers recognize that cometary tails always point away from the sun, regardless of the comet's direction of motion. Not until the 20th century was this fact explained radiation pressure and solar wind push material outward, creating the characteristic streaming appearance. 3I/Atlas is not called a comet. The official designation identifies it as an interstellar object, a category that includes both asteroidal and cometary types. The distinction matters less than expected. The boundary between asteroids and comets is blurry. Some asteroids outgas, some comets appear inert. The difference is more about activity than composition. If it produces a coma or tail, it gets called a comet. If it does not, it is an asteroid. 3I/Atlas is now producing a tail. Whether that makes it a comet is a question of semantics rather than physics. The tail forming around 3I/Atlas on November 11th is not yet visible to the unaided eye. It would not be visible even if the object were much closer. The dust density is too low, the reflected light too faint, but through telescopes equipped with sensitive cameras, after image processing that enhances faint structures, the tail appears as a subtle elongation in the anti-sunward direction. The tail extends approximately 50,000 kilometers, roughly 4 Earth diameters, before fading into the noise floor of detection. Only took a few tons of dust spread across 50,000 kilometers to create something barely detectable. Space is good at dilution. The dust grains in the tail are sorted by size. This happens automatically, a consequence of how radiation pressure acts on particles of different masses. Radiation pressure force is proportional to the grain's cross-sectional area proportional to radius squared. Gravitational force is proportional to mass proportional to radius cubed for spherical grains. The ratio of radiation pressure to gravity therefore goes as 1 over radius. Smaller grains experience stronger acceleration relative to their mass. The result is a tail where the smallest grained sub-micrometer particles rush outward fastest, forming the tail's outer edge. Larger grains millimeter-sized or bigger lag behind, forming a denser inner region closer to the nucleus. Very large grains, centimeter-sized or larger, barely leave the nucleus at all, falling back to the surface after being lofted by gas pressure. The tail thus becomes a natural particle sorter, separating grains by size through purely physical processes. The tail's shape encodes information about the outburst history. Dust ejected during the November 10th brightening event now occupies a specific region along the tail. Dust ejected earlier, during the November 3rd event, has travelled farther forming a separate structure that may or may not be distinguishable from newer material. Each subsequent outburst adds another layer, another component to the tail's structure. Reading the tail is like reading tree rings. Each layer marks a specific time, a specific event, except that tails disperse. Solar wind turbulence scrambles the neat layering. Variations in radiation pressure due to the object's changing distance from the sun alter acceleration rates. The tail is not a stable structure but a dynamic one, constantly evolving, mixing, spreading. After weeks, the temporal information becomes blurred. After months, it is lost entirely. The tail also contains information about the dust's optical properties. How efficiently grains scatter light depends on their size relative to the wavelength of light. Grains much smaller than a wavelength scatter light, according to Rayleigh. Scattering efficiency increases strongly with decreasing wavelength, making the scattered light bluer. Grains much larger than a wavelength scatter light, geometrically wavelength becomes irrelevant, and the scattered light has the same colour as the incident light. Grains comparable to the wavelength scatter light through Mie scattering, which produces complex wavelength dependencies. Observations of 3I/Atlas's tail in multiple wavelength bands reveal that the dust is reddish. It scatters longer wavelengths more efficiently than shorter wavelengths. This suggests the grains are either very small, in the submicrometer range where Rayleigh scattering begins to dominate, or they're composed of materials that absorb blue light preferentially. Many organic compounds are red. Many iron-bearing minerals are red. The colour alone does not uniquely identify composition, but it constrains the possibilities. Only took light at different wavelengths to reveal something about grain size and composition. Photons are remarkably informative when interrogated properly. The dust production rate can be estimated from the tail's brightness. The calculation requires assumptions about grain size distribution, albedo, and scattering efficiency, but reasonable assumptions yield estimates. During the November 10th outburst, 3I/Atlas likely released between 5 and 10 kilograms of dust per second at peak activity. Over the 12-hour peak period, total dust mass released was perhaps 200 to 400 tons. This is not a large mass loss. The object's total mass, assuming a 2-kilometer diameter and 1 gram per cubic centimeter density, is approximately 4 billion tons. Losing a few hundred tons represents 1 part in 10 million of the total mass. At this rate, the object could sustain active outgassing for years without significantly depleting its mass. But the outgassing is not continuous. It comes in bursts correlated with solar wind events. If such events occur once per week during solar maximum, total mass loss over a year might be 10,000 to 20,000 tons, still only 1 part in 200,000 of the total. Comets orbiting the Sun lose mass continuously when near perihelion. Short-period comets like Halley lose millions of tons per orbit. They survive dozens or hundreds of orbits before depleting their volatiles, ending their active lives as dormant nuclei that resemble asteroids. 3I/Atlas will not orbit. It will make a single pass through the inner solar system and then leave forever. Whatever mass it loses during this passage is lost permanently, never to be replenished. A one-time expenditure as the object moves from one interstellar journey to another. The tail is not just dust. Gas is also present, though harder to detect. Gas does not scatter light efficiently unless it fluoresces, absorbs sunlight, and re-emits it at specific wavelengths. Water vapor fluoresces weakly in visible light but more strongly in ultraviolet. Hydroxyl radicals, produced when ultraviolet light breaks apart water molecules, fluoresce in ultraviolet and visible wavelengths. Carbon monoxide fluoresces in ultraviolet. Detecting these emissions requires spectroscopy, ideally with space-based telescopes that can observe ultraviolet wavelengths blocked by Earth's atmosphere. No space-based observations of 3I/Atlas have been scheduled yet. Ground-based observations continue, but they cannot see ultraviolet emissions. The gas composition remains largely unknown. The sodium emission provides one clue: sodium is present, but sodium is a minor component. The bulk gases, whatever they are, remain invisible to current observations. Only took a lack of UV-capable telescopes pointed in the right direction to leave this question unanswered. Logistics matter as much as physics sometimes. The gas tail, if it exists at a detectable level, should point more directly away from the sun than the dust tail. Solar wind magnetic fields sweep gas downstream faster than radiation pressure pushes dust. The angle between dust and gas tails can reveal information about solar wind speed and magnetic field orientation at the object's location. But without clear gas detection, this diagnostic tool remains unavailable. Some researchers propose using radio telescopes to detect gas. Water molecules emit at specific radio frequencies. Hydroxyl radicals emit at 18 centimeters wavelength, a transition extensively studied in comets and molecular clouds. If 3I/Atlas produces enough gas, radio telescopes might detect it even if optical observations cannot. Proposals are submitted to facilities like the Very Large Array and ALMA. Observing time is requested. Committees deliberate. Meanwhile, the tail grows. Each passing day, more dust escapes into space. The tail lengthens, fades, disperses. Weeks from now, the dust from these November outbursts will have spread across millions of kilometers, diluted to invisibility, scattered into the solar system's vast inventory of interplanetary dust. The particles will continue outward, some eventually escaping the solar system entirely, others falling into the sun over timescales of thousands of years, most simply drifting in orbits that will never bring them near another human observer. The tail is ephemeral. It exists now, visible to those who look carefully. Then it dissipates into memory and archived data. The object continues forward. The tail is left behind, a trail marking where 3I/Atlas has been, not where it is going. Magnetic fields are invisible. They exert no direct force on neutral matter. A magnetic field of any strength can pass through rock, ice, or human flesh without deflection or absorption. Only charged particles respond: electrons, protons, ions, their trajectories curved by the Lorentz force, which acts perpendicular to both the particle's velocity and the field direction. This makes magnetic fields difficult to visualize, but essential to understanding how plasma behaves in space. The magnetic cloud that passed 3I/Atlas on November 10th carried a field structure that can be described mathematically but not easily pictured. The field lines wrapped in helical patterns around a central axis, like threads in a rope. The field strength varied from 20 nanotesla at the edges to 50 nanotesla at the core. The field direction rotated smoothly over the 12 hours the cloud took to pass, starting with field lines pointing northward, rotating through westward, southward, eastward, and back to northward. This rotation is the signature of a flux rope, a coherent magnetic structure produced when plasma and field erupt together from the sun's corona. Spacecraft passing through such structures record the rotation in their magnetometer data. For 3I/Atlas, no magnetometer is present. The object experiences the field without measuring it, responds to it without recording it, is affected by forces that leave no direct trace. What remains is indirect evidence: brightness changes, emission lines, patterns in light curves that suggest something happened even if the exact mechanism remains uncertain. Only took 12 hours for the magnetic field to rotate through 180 degrees. The plasma carried frozen-in field lines past the object like a river carrying leaves downstream. Charged particles in the solar wind do not move in straight lines through magnetic fields. They spiral. The radius of the spiral depends on the particle's energy and the field strength. For a proton with solar wind energy, around 1 kilo-electron-volt in a 50 nanotesla field, the gyro radius is approximately 100 kilometers. This means particles spiral along field lines with loops 100 kilometers in diameter while drifting parallel to the field at hundreds of kilometers per second. When these spiraling particles encounter 3I/Atlas, a 2-kilometer obstacle, they do not collide directly. Most pass by, their trajectories deflected by the object's presence. Some strike the surface. The ones that strike transfer their kinetic energy to surface atoms, heating microscopic regions through impact. Over hours, billions upon billions of impacts accumulate enough energy to warm macroscopic areas. But magnetic fields affect not just individual particles, but collective plasma behavior. Plasma contains equal numbers of positive and negative charges. When plasma flows past an obstacle, electric currents can form at the interface. These currents generate magnetic fields that oppose the external field, creating a magnetic barrier that deflects incoming plasma around the obstacle. This is how Earth's magnetosphere works. Currents in the magnetopores create a magnetic barrier that shields the planet from direct solar wind impact. 3I/Atlas has no global magnetic field. Spacecraft passing near it, if any had been available, would detect no dipole field, no magnetosphere. But local magnetic fields could still exist if the object contains magnetized materials. Some meteorites carry remnant magnetization fossil magnetic fields frozen into iron-nickel grains when these grains cooled below the Curie temperature in the presence of a magnetic field. If 3I/Atlas contained such materials, fragments from a differentiated parent body's core, then patches of its surface might carry weak magnetic fields. These patches, if they exist, would interact with the solar wind's magnetic field. Field lines from the solar wind would connect to field lines anchored in the object's surface. The connection points are regions where magnetic stress concentrates, where charged particles can be accelerated to higher energies, where heating occurs more efficiently. This mechanism, magnetic reconnection at small scales, could explain why outgassing appears localized rather than uniform across the surface. Only took magnetized grains a few micrometers across to create local field anomalies. Small-scale structure matters in plasma physics. Another possibility involves electric charging. Objects in space do not remain electrically neutral. Photons striking the surface knock electrons free through the photoelectric effect. Solar wind electrons strike the surface and sometimes stick. Solar wind protons strike and embed themselves. The balance between electron emission and collection determines the object's net electric charge. For objects at 3I/Atlas's distance from the Sun, surfaces typically charge to a few volts positive relative to the surrounding plasma. A charged object in a flowing plasma experiences forces. The plasma tries to neutralize the charge by delivering opposite charge particles to the surface. Electric fields around the charged object deflect particle trajectories, focusing some particles toward the surface while repelling others. The net result is enhanced particle flux to specific regions, creating hotspots where heating is more intense. The charging is not uniform across the surface. Areas illuminated by the sun emit more electrons through the photoelectric effect and charge more positive. Shadowed areas, receiving fewer photons, charge less or remain neutral. As 3I/Atlas rotates, the charging pattern rotates with it. Hotspots move across the surface, driving outgassing that varies with rotation phase. This model explains several observations. The correlation between brightening and solar wind events enhance plasma flux increases charging and heating. The periodic variations during outburst rotation carries active regions into and out of favorable configurations. The delay between shock arrival and peak brightness charging and heating take time to accumulate. But the model makes predictions that remain untested. If surface charging drives the activity, then the effect should depend on solar illumination angle. Regions facing the sun should be more active than the regions on the night side. Observations have not yet confirmed or refuted this. The data quality and temporal coverage are insufficient to distinguish between models. More observations are needed. more detailed light curves, more spectroscopy, more coverage across rotation phases, only took centuries of studying comets before scientists admitted they still do not fully understand how cometary activity works. 3. I/Atlas adds another layer of complexity to an already incomplete picture. Dust grains released from the surface also interact with magnetic fields, but only if the grains carry electric charge. Dust in space typically charges through the same mechanisms as larger objects' photoelectric emission and plasma collection. The charge-to-mass ratio for dust grains is higher than for bulk objects, meaning electromagnetic forces can compete with gravity even for relatively weak fields. Charged dust grains gyrate around magnetic field lines just as charged particles do. But the gyro radius is much larger because of the grain's higher mass. For a micrometer-sized dust grain carrying charge of a few hundred electrons, the gyro radius in a 50 nanotesla field is approximately 1 million kilometers. This means the grains spiral loosely along field lines, while drifting outward due to radiation pressure. The interplay between radiation pressure, which pushes grains away from the sun, and magnetic forces, which constrain motion along field lines, creates complex trajectories. Dust does not simply stream straight back from the object. Instead, it curves, spirals, and sometimes even loops before eventually escaping. The tail's shape encodes information about magnetic field geometry if the observations are good enough to resolve the structure. Current observations are not good enough. The tail appears as a simple elongation, a diffuse glow with no discernible internal structure. Perhaps higher resolution imaging would reveal complexity. Perhaps not. The dust density may be too low for structure to be visible, even with the best instruments. The magnetic field in the solar wind is not static. It fluctuates on all timescales, from seconds to days. Turbulence generates eddies and waves that propagate through the plasma. Magnetic islands, closed loops of field disconnected from the sun, drift outward, each carrying a pocket of plasma with different properties than the surrounding medium. Shocks from multiple coronal mass ejections interact, merge, and create regions of compressed plasma with tangled magnetic fields. 3I/Atlas moves through this complex environment like a leaf in a turbulent stream. One moment, the field points north, the next, it points east, then south, then it reverses. The particle flux varies by factors of 2 or 3 on timescales of minutes. The temperature fluctuates, the pressure pulses, the object experiences all of this passively, without control, without agency, responding as its composition and structure dictate. Scientists try to reconstruct this environment using models of solar wind propagation. They track coronal mass ejections from the sun through interplanetary space, predicting arrival times and field orientations. The predictions are imperfect. The solar wind is chaotic. Small differences in initial conditions grow into large differences in outcomes. Forecasts accurate to within a day at Earth's orbit become uncertain to within several days at 3I/Atlas's distance. The reconstruction is approximate, probabilistic, subject to revision as more data arrives. Still, the effort continues. Each observation of 3I/Atlas is paired with observations of the Sun, with measurements of solar wind at Earth and at other spacecraft. The goal is to correlate object behavior with environmental conditions, to find patterns that reveal cause and effect, to build understanding from fragments of information scattered across space and time. November 14th arrives without ceremony. The Sun rotates, carrying active regions across its visible hemisphere. One region, AR 3895, emerges near the eastern limb, a cluster of sunspots that grows rapidly over 48 hours. By November 16th, the region spans 150,000 kilometers and displays beta-gamma magnetic configuration. The magnetic field lines are tangled, stressed, storing energy that will eventually be released. The release comes on November 17th at 14:23 UTC, and X3. One flare erupts from AR 3895, the most powerful flare of solar cycle 25 so far. The flare's X-ray emission saturates detectors on multiple satellites. Shortwave radio communications across Earth's sunlit hemisphere fade to static. GPS signals degrade. The electromagnetic pulse reaches Earth in 8 minutes, but the real event is what follows. A coronal mass ejection launches 90 minutes after the flare peak. Coronagraph images show a partial halo. The ejection is directed somewhat toward Earth, but also southward, below the ecliptic plane. Initial speed estimates suggest 1,200 kilometers per second. Fast. Massive. The mass involved exceeds 3 billion tons. The magnetic field embedded in the ejection measures 80 nanotesla at the source, likely stronger once compressed by the shock wave that forms ahead of it. Only took one active region to produce this. The Sun at solar maximum is generous with its violence. Forecasters calculate the ejection's trajectory. It will reach Earth in approximately 36 hours. Geomagnetic storm warnings are issued. Aurora watchers in high-latitude regions prepare for displays. Satellite operators review contingency plans. Power grid managers are notified. But the ejection's southward component means it will also pass near 3I/Atlas, currently at 4.2 astronomical units and continuing its inward drift. The object does not receive warnings. It continues tumbling through space, its surface temperature slowly rising as solar distance decreases. Sublimation of volatiles continues at low levels, creating a faint coma barely detectable even with large telescopes. The November 10th outburst has faded. Brightness has returned nearly to baseline, though again with a slight residual enhancement. The dust tail persists, now extending 70,000 kilometers but fading as older dust disperses. Observers monitoring 3I/Atlas note the approaching coronal mass ejection. Predictions suggest arrival on November 19th, approximately 60 hours after launch. The uncertainty in arrival time is plus or minus 12 hours. The uncertainty in impact intensity is larger. Whether the ejection will pass directly over the object or just graze it makes an enormous difference in the effect produced. Telescope time is requested for intensive monitoring during the predicted arrival window. Some requests are approved. Networks of amateur astronomers are alerted. Distributed observations can fill gaps when professional facilities are unavailable. The community responds. Dozens of telescopes, ranging from backyard instruments to university observatories, add 3I/Atlas to their observing schedules. Only took the prospect of something dramatic to mobilize this level of coordination. Scientists are human. They enjoy watching things happen. The coronal mass ejection travels outward, its speed gradually decreasing as it plows through the ambient solar wind. The shockwave ahead of it accelerates energetic particles. Solar protons with energies of tens to hundreds of mega-electron-volts stream outward along magnetic field lines, reaching Earth's orbit within hours of the flare. These particles spiral along field lines with nearly the speed of light, able to traverse 5 astronomical units in less than an hour. If 3I/Atlas were inhabited, if it carried electronic systems, the arriving energetic particles would pose a radiation hazard. Silicon chips malfunction when struck by high-energy protons. Biological tissue accumulates radiation damage. Spacecraft designers plan around this, using shielding and radiation-hardened components. But 3I/Atlas is just rock and ice. Radiation passes through without consequence. Atoms are ionized. Bonds are broken. But these effects are negligible compared to billions of years of cosmic ray exposure the object has already endured. The shockwave arrives at Earth on November 19th at 03:15 UTC. Magnetometers on ground stations and satellites detect the sudden increase in magnetic field strength. Solar wind speed jumps from 400 to 800 kilometers per second. Density increases 5-fold. The Earth's magnetosphere compresses. Auroras flare across the high latitudes. visible as far south as Colorado and northern Spain. The geomagnetic storm reaches G4 level on the 5-point scale severe but not extreme. At 3I/Atlas, the arrival time is less certain. The ejection's southward trajectory means it must travel slightly farther to reach the object's position. The prediction is November 19th evening. Perhaps 6 hours after Earth impact, observers wait. Telescopes track the object continuously through the night. Light curves are recorded minute by minute. The brightening begins at 21:47 UTC, not suddenly but as a gradual increase. Brightness rising 5% over 20 minutes, then the rate accelerates. By 22:30, brightness has increased 30%, by 23:00, 50%. The increase continues. By midnight UTC on November 20th, 3I/Atlas shines at twice its pre-event brightness. Only took 2 hours to double in brightness, faster than the November 10th event, more intense. Spectroscopy reveals sodium emission again. Stronger than before. The D lines are bright, saturating in some spectra. Other emission lines begin appearing neutral oxygen at 630 nanometers. Faint but present. Potassium emission at 766 nanometers. Marginal but above noise. The spectrum is changing, revealing species not detected in previous outbursts. The light curve shows structure. Superimposed on the overall brightening are oscillations with periods of 1 to 2 hours. The oscillations are not noise they repeat, with phase coherence suggesting a physical origin. Perhaps rotation brings active regions into view periodically. Perhaps the outgassing itself is pulsing, driven by cyclic processes in subsurface pressure build-up and release. The data does not yet distinguish between possibilities. By 0200 UTC on November 20th, 6 hours into the event, brightness reaches a peak at 2.3 times baseline, then it plateaus. For 4 hours, brightness remains nearly constant, fluctuating by only a few percent around the peak value. The plateau suggests equilibrium outgassing rate balances whatever drives it. Energy input from the solar wind matches energy loss through sublimation and radiation. During the plateau, the sodium emission reaches maximum intensity. The emission is strong enough that observers can measure Doppler shifts in the spectral lines. The sodium appears redshifted on one side of the object and blue shifted on the other, the signature of expanding gas flowing outward from the nucleus. The expansion velocity is approximately 500 meters per second, consistent with sublimation-driven outflow from a moderately warm surface. Only took high-resolution spectroscopy to reveal that the gas is actually moving, not just present. Doppler shifts carry information photometry alone cannot provide. The oxygen emission suggests water is involved. Oxygen atoms come from water molecules broken apart by solar ultraviolet light. H2O splits into hydroxyl and atomic hydrogen. Then hydroxyl splits into atomic oxygen and hydrogen. The oxygen atoms, once liberated, scatter sunlight and produce the observed emission. The presence of oxygen emission confirms that water vapor is being released, even though water vapor itself has not been directly detected. The dissociation products serve as tracers. The potassium emission is more puzzling. Potassium is less abundant than sodium in most cosmic materials, yet the emission is strong enough to detect. Either 3I/Atlas is enriched in potassium relative to typical solar system objects, or the potassium is concentrated in specific minerals that are being preferentially released. Potassium-bearing minerals include feldspars and certain clay minerals. The emission hints at silicate dust composition, but the interpretation is ambiguous. At 0600 UTC, the plateau ends, brightness begins declining, not rapidly but steadily. Over the next 12 hours, brightness decreases from 2.3 times baseline back toward 1.5 times baseline. The decline is not smooth, small fluctuations continue, suggesting active regions still rotate into and out of view. but the overall trend is downward. By November 21st, 36 hours after the brightening began, brightness has stabilized at 1.4 times baseline, higher than before the event, higher than after the November 10th event. Each outburst leaves the object slightly brighter than it was before, as if successive events are liberating more dust that remains in the surrounding coma, accumulating over time. The dust tail, imaged during the outburst's peak, shows dramatic enhancement. The tail now extends 120,000 kilometers, nearly doubling in length within hours. New dust fills the inner tail, bright and concentrated near the nucleus. Older dust from previous events occupies the outer tail, fainter and more dispersed. The tail's structure shows clear layering, different components distinguishable by their brightness profiles. Only took the most intense solar wind event of the cycle to produce the most dramatic brightening. The correlation is no longer ambiguous. Questions accumulate faster than answers. Each observation resolves one uncertainty and introduces three more. The correlation between solar wind events and brightness changes is now well established. No one disputes this. But correlation is not explanation. The mechanism by which solar wind energy reaches subsurface volatiles and triggers outgassing remains debated. Multiple hypotheses compete, each consistent with some observations, each contradicted by others. The electromagnetic induction hypothesis suggests that magnetic fields in coronal mass ejections induce electric currents in conducting regions within 3/Atlas. The currents generate heat through resistive dissipation. The heat warms subsurface ices. The ices sublimate. Gas escapes, carrying dust. Brightness increases. This model explains the correlation with magnetic clouds, the delayed response, and the sustained brightening during events. But it requires that the object contain enough conducting material for significant currents to flow. No direct measurement of 3I/Atlas's electrical conductivity exists. The requirement remains an assumption. The particle bombardment hypothesis suggests that energetic particles from the solar wind directly heat the surface. Protons and electrons with energies of tens to hundreds of kiloelectron volts penetrate the top few millimeters of the surface, depositing their energy as heat. The accumulated heating warms near-surface ices, triggering sublimation. This model explains why events with higher particle flux produce stronger brightenings, but it struggles to explain why brightening continues for hours after the initial shock passage. Particle heating should peak quickly and decline as particle flux decreases. Only took decades of studying comets before scientists realized that surface heating alone cannot explain everything comets do. Subsurface processes matter. A third hypothesis proposes that 3/Atlas contains pressurized subsurface voids. Gas accumulates in these voids over time as deep ices slowly sublimate from interior warmth. The voids are sealed by overlying layers of dust and refractory material. When surface heating increases during solar wind events, the seal weakens, cracks form, pressurized gas escapes explosively, carrying dust with it. This model explains the rapid onset of brightening and the oscillations observed in light curves. Each oscillation represents a discrete outburst as a new void depressurizes, but it requires complex interior structure, layering, and mechanical properties that cannot be verified remotely. A fourth hypothesis invokes electrostatic dust levitation. Solar wind plasma charges the surface. Electric fields form between the charged surface and dust grains sitting on it. If the electric field becomes strong enough, it overcomes gravity and magnetic cohesion, lifting dust into the surrounding space. The lofted dust scatters sunlight, increasing brightness. This model explains why brightening can occur rapidly and why it correlates with enhanced plasma flux. But calculations suggest that electric fields strong enough to levitate dust require particle fluxes higher than observed during typical solar wind events. Unless the dust grains are unusually small or the surface conductivity is very low, None of these hypotheses is clearly wrong, none is clearly right. Each contains elements of truth, and the real process likely involves multiple mechanisms operating simultaneously. Surface heating contributes, electromagnetic induction might contribute if conductive paths exist. Subsurface pressure could drive some outbursts. Electrostatic effects might loft some fraction of the dust. Disentangling the contributions of each mechanism requires more detailed observations than currently available. Only took 3 major outburst events to make clear how little is actually understood. Knowledge and ignorance grow together. The composition of 3I/Atlas remains poorly constrained. Spectroscopy reveals sodium, potassium, oxygen, and sunlight reflected from dust. But these observations sample only the material being actively released, a bias sample that may not represent the bulk composition. The deep interior might be entirely different from the surface layers. Comets often show this dichotomy. Surfaces are processed by radiation and thermal cycling, darkened and depleted in volatiles. Interiors remain pristine, retaining the composition from formation. A thin surface layer can hide what lies beneath. The object's density, estimated at approximately 1 gram per cubic centimeter, suggests high porosity. Solid ice has a density of 0.9 grams per cubic centimeter. Solid rock has densities ranging from 2 to 3 grams per cubic centimeter. A mixture of ice and rock at 1 gram per cubic centimeter implies either that the object is nearly pure ice with trace rock, or that it contains substantial voids. The latter seems more likely. Porous structures are common in comets and some asteroids, rubble pile asteroids. Collections of fragments loosely bound by gravity can have porosities exceeding 50%. High porosity has implications for how the object responds to heating. Porous materials insulate their interiors. Heat deposited at the surface conducts inward slowly. Thermal diffusion timescales increase with depth squared, meaning that heating 1 meter below the surface takes 100 times longer than heating 1 centimeter below. This limits how deeply solar wind heating can penetrate on the timescales of a single event. Most of the action happens in the top few centimeters or less, but porous structures also allow gas to flow. When volatiles sublimate in subsurface voids, the gas must escape to the surface, and flow through porous media follows Darcy's law, which relates flow rate to pressure gradient and permeability. If permeability is low, gas builds up pressure before finding pathways out. If permeability is high, gas escapes freely without pressure buildup. The difference affects outgassing behavior. Low permeability produces episodic bursts. High permeability produces steady outflow. Only took engineers centuries to figure out groundwater flow. The same principles apply to gas flow in cometary nuclei, though no one builds wells in comets. The rotation period of 7.3 hours is slow for an object of this size. Typical small bodies rotate faster, with periods of hours to minutes. Slow rotation could result from several factors. The object might be elongated, with high moment of inertia that resists rotational acceleration. It might have been spun down by outgassing torques. Gas jets exert forces that can alter rotation rates over time. Or it might have experienced a collision or tidal encounter in the past that modified its spin state. The complex rotation, with precession on 30-day timescales, confirms that the object is not a simple sphere. Irregular shapes precess because angular momentum points in a fixed direction, while the object's moment of inertia tensor varies with orientation. The precession period depends on the shape's asymmetry and the rotation rate. Larger asymmetry and faster rotation produce shorter precession periods. The 30-day precession of 3I/Atlas suggests moderate asymmetry, perhaps an elongation ratio of 2:1, or a traxial ellipsoid with axes differing by 30%. Shape affects how sunlight and solar wind flux distribute across the surface. A spherical object illuminates uniformly at a given solar zenith angle. An elongated object has regions near the poles that receive less flux than equatorial regions. If active regions are preferentially located near the poles or equator, rotation and precession modulate their exposure to solar wind, creating periodic variations in outgassing rate. Determining the object's actual shape requires either resolved imaging or detailed light curve modelling. Resolved imaging is impossible at current distances, with current telescopes 3 Y/Atlas subtends an angular size of approximately 0.01 arcseconds, far below resolution limits. Light curve modelling is possible but requires extensive data across multiple rotation periods and viewing geometries. The data collected so far is insufficient. More time, more observations, more patience. Some researchers propose sending a spacecraft to 3 I/Atlas. The object's hyperbolic trajectory means any mission would be a flyby, not a rendezvous. Launch windows are narrow. Flight times would be years. But the scientific return from close-up observations of an interstellar object would be enormous. Resolved images of the surface, in situ measurements of gas composition, magnetic field measurements, dust collection, direct sampling of material that formed in another star's planetary system, only took a few preliminary calculations to show that any such mission would require launch within the next 6 months to have a chance of intercept. No mission is ready. No spacecraft exists. The opportunity will pass. 3 I/Atlas will leave the inner solar system, accelerate outward beyond Neptune's orbit, and return to interstellar space, never to be visited by human technology. The decision not to pursue a mission is one of practicality, not desire. Spacecraft take years to design and build. Funding must be secured. Instruments must be developed. Launch vehicles must be booked. The entire process, even on an accelerated schedule, takes longer than the time available. By the time a mission could launch, the object would be too far, moving too fast, requiring more propulsion than any existing rocket can provide. So the study of 3 I/Atlas remains remote. Telescopes on Earth and in orbit, photons as the only messengers, spectra as the only information carriers. Scientists work with what they have, extracting every bit of information from each observation, building models that fit the data as well as possible while acknowledging the gaps in understanding. The object does not care about these limitations. It continues inward, responding to solar wind as it always has, following the trajectory gravity dictates, indifferent to the curiosity it generates among observers 93 million miles away on a blue planet that it will never approach more closely than Jupiter's orbital distance. The heliosphere is not uniform. It is a structure, a geography, though empty of landmarks. Solar wind flowing outward at variable speeds creates regions of compression and rarefaction. Fast wind overtaking slow wind creates corrotating interaction regions, zones where plasma piles up. Magnetic fields strengthens, and particle densities increase. These interaction regions rotate with the Sun because they originate from solar structures that rotate every 27 days, as seen from Earth. The same interaction regions sweep past, producing quasi-periodic variations in solar wind conditions. During solar maximum, corrotating interaction regions become less organized. The Sun's magnetic field is too chaotic, active regions too distributed, for clear, fast and slow wind streams to establish themselves. Instead, the solar wind is lumpy, turbulent, filled with transient structures from successive coronal mass ejections. These ejections overtake one another, merge, and create complex multi-shock systems that propagate outward, like ripples colliding on a disturbed pond. 3 I/Atlas moves through this lumpy medium. The object does not follow a simple path through uniform conditions. Instead, it encounters pocket after pocket of different plasma states, dense slow wind, dilute fast wind, shocked regions, magnetic clouds, turbulent boundary layers. Each region subjects the object to different conditions. The response varies accordingly. Only took one solar maximum to make the heliosphere more interesting and more complicated than models predicted. Nature resists simplification. On November 23rd, solar wind monitors at Earth detect a weak shock from a coronal mass ejection launched 3 days earlier. The ejection is not dramatic, no strong flare accompanied it. The mass involved is modest. The speed is only 600 kilometers per second. But the trajectory carries it through the region where 3I/Atlas now resides, at 4.1 astronomical units and continuing inward. The object's brightness, which had stabilized after the November 17th event, begins increasing again on November 24th. The increase is modest 20% over baseline, not the doubling seen during stronger events. Spectroscopy shows sodium emission, weaker than before. The light curve lacks the sharp peak and plateau structure of previous events. Instead, brightness rises gradually over 12 hours, holds steady for 8 hours, then declines gradually over another 12 hours. The event is unremarkable compared to earlier outbursts. But it contributes another data point. Another correlation between solar wind disturbances and brightness increases. Another confirmation that the pattern holds across a range of intensities. Weak solar wind events produce weak brightenings. Strong events produce strong brightenings. The relationship appears roughly linear, though the scatter in the data is large enough that nonlinear models cannot be ruled out. Researchers compile the observations into a light curve spanning 3 weeks. The baseline brightness has been increasing slowly, a trend independent of the discrete outburst events. This slow brightening likely reflects the object's decreasing distance from the Sun. As 3I/Atlas approaches perihelion, solar heating increases, even if gradually. The increased heating drives low-level continuous sublimation, creating a persistent coma that adds to the reflected light. The discrete outbursts from solar wind events are superimposed on this slowly rising baseline. Separating the two components, gradual brightening from solar heating and rapid brightening from solar wind events, requires careful modeling. The solar heating component can be estimated from the object's distance and assumed thermal properties. The residual, after subtracting the solar heating trend, represents the contribution from solar wind disturbances. The residuals show clear spikes coinciding with predicted arrivals of coronal mass ejections, confirming that solar wind is the primary driver of the discrete brightening events. Only took 3 weeks of data to establish what would have been impossible to see in a single observation. Time series matter. The dust tail continues to grow. By late November, it extends nearly 200,000 kilometers, easily visible in processed images from mid-sized telescopes. The tail's brightness profile shows layering brighter regions corresponding to recent dust releases, dimmer regions from older material, the newest dust from the November 17th and 24th events occupies the inner 50,000 kilometers. Older dust from November 10th and 3rd extends farther out, now dispersed and fading. The tail's orientation is almost exactly anti-sunward. This confirms that radiation pressure dominates the dust dynamics. If solar wind drag was significant, the tail would curve backward, trailing behind the object's orbital motion. No such curvature is visible at current resolution. Either the dust grains are large enough that radiation pressure far exceeds drag forces, or the solar wind at this distance is too tenuous to produce measurable drag. Both factors likely contribute. The tail's length of 200,000 kilometers is respectable but not extraordinary. Active comets near 1 astronomical unit commonly develop tails millions of kilometers long. But those comets are closer to the Sun, where radiation pressure is stronger and dust production rates are higher. For an object at 4 astronomical units producing modest amounts of dust, a tail of this length is appropriate. The tail does not point perfectly anti-sunward. Careful measurements reveal a slight offset, a few degrees, possibly due to aberration effects. The Sun's light carries momentum. But the source of that light is not where the sun appears to be, it is where the sun was 8 minutes ago when the photons were emitted. During those 8 minutes, 3I/Atlas moves along its trajectory, changing its position relative to the sun. The tail points away from where the sun was, not where it currently is. The difference is small, usually negligible, but measurable with precise astrometry. Only took photons 8 minutes to travel from sun to object. In that time, the object moved 20 kilometers. The geometry encodes motion that would otherwise require multiple observations to detect. Amateur astronomers contribute observations that fill gaps in professional coverage. One observer in Australia images the object nightly using a 30-centimeter telescope and a sensitive CCD camera. Another in New Mexico uses a 40-centimeter telescope and tracks the object for hours each night, recording brightness every few minutes. A group in Italy coordinates their observations, timing them to cover different rotation phases. The data they collect is not as precise as professional observatory data, but it is more continuous, with fewer gaps. The amateur community has embraced 3I/Atlas as a target. Interstellar objects are rare. Only 3 have been identified so far, 1I/Oumuamua in 2017, 2I/Borisov in 2019, and now 3I/Atlas in 2025. Each was observable for only a limited time before fading beyond reach. Each generated enormous interest. Amateur astronomers with the equipment and skill to contribute do so eagerly, knowing they are participating in something that happens perhaps once per decade. The data they provide is valuable. Professional observatories cannot observe every night. Weather, maintenance, competing projects, and funding limitations create gaps. Amateur observations fill those gaps, providing continuity that would otherwise be lost. When the data is compiled, amateur contributions account for more than half the total observing time on 3I/Atlas during November. Their efforts make possible light curve analysis that would otherwise lack sufficient temporal coverage. Collaboration between professional and amateur astronomers is not new. It has a long history in comet studies, supernova searches, variable star monitoring, and asteroid tracking. The relationship is symbiotic. Professionals provide theoretical context, detailed analysis, and access to specialized equipment. Amateurs provide observing hours, geographical coverage, and enthusiasm. Both benefit. Science advances faster than either group could achieve alone. Only took the internet to make coordination feasible. Decades ago, organizing distributed observations required telephone calls, letters, and scheduled meetings. Now, email lists, online forums, and shared data repositories enable real-time collaboration across continents. On November 28th, another coronal mass ejection is observed leaving the Sun. The source is AR 3902, a new active region near the central meridian. The ejection is fast, 1,000 km per second, and appears to be directed along the ecliptic plane. Initial trajectory analysis suggests it might pass near 3Y/Atlas. Now, at 4.0 astronomical units. Predicted arrival is November 30th. Observers are alerted. Telescope schedules are adjusted. The community prepares for what might be the 4th major brightening event. If it occurs, it will provide the strongest test yet of the correlation between solar wind intensity and object response. The November 17th event was the most intense so far. If this event exceeds it, and if the brightness increase is correspondingly larger, the linear relationship would be further confirmed. If the relationship is nonlinear, departures from proportionality might become evident. The wait begins, 2 days until predicted arrival. Nothing to do but watch, monitor, and record. The object continues forward, indifferent to predictions, responding only to what actually reaches it, not to what might reach it. The universe operates on actuality, not anticipation. Spectroscopy is the art of splitting light into its component wavelengths. Newton demonstrated this with a prism in 1666 separating white light into a rainbow. By the 19th century, scientists had realized that the rainbow contains information dark lines where specific wavelengths are absorbed, bright lines where they are emitted. Each chemical element produces a unique pattern of lines, a fingerprint readable in starlight. Sodium produces 2 bright yellow lines spaced 6 angstroms apart. Hydrogen produces a series of lines in red, blue, and violet. Iron produces hundreds of lines scattered across the spectrum. The spectrum of 3I/Atlas is mostly a reflected solar spectrum. The sun's light contains dark absorption lines, where elements in the solar photosphere absorb specific wavelengths. When that light bounces off 3I/Atlas and reaches Earth, it carries those same absorption lines, but superimposed on the reflected spectrum are features unique to the object emission lines from gas in the coma, absorption bands from dust composition, subtle shifts that reveal motion. The sodium D lines at 589 nanometers are the strongest emission features detected. These lines appear bright, standing above the continuum of reflected sunlight. Their intensity varies with time, correlating with brightening events. During the November 17th outburst, the sodium emission was bright enough that its wings, the broad bases of the emission lines, became visible, revealing Doppler broadening from gas moving at hundreds of meters per second. Only took photons at 2 specific wavelengths to reveal that sodium atoms are escaping the object. Everything else about the gas remains inferred or unknown. Oxygen emission at 630 nanometers appears intermittently. This line, the so-called forbidden transition of neutral oxygen, requires low-density environments to occur. In Earth's atmosphere, collisions de-excite oxygen atoms before they can emit. In space, densities are low enough that atoms remain excited long enough to radiate. The presence of this line confirms that oxygen atoms exist in 3I/Atlas's coma, and that the coma is indeed a low-density environment where collisions are rare. The oxygen comes from water. Solar ultraviolet photons break water molecules into hydrogen and hydroxyl radicals. Further photodissociation splits hydroxyl into oxygen and hydrogen. The process is called photodissociation, and it occurs in all cometary comae exposed to sunlight. The oxygen atoms produced this way scatter sunlight at specific wavelengths, producing the observed emission. Detecting oxygen emission is indirect evidence for water vapor even when water itself is not directly observed. Water vapor has spectral lines in the infrared, near 3 micrometers wavelength. Ground-based telescopes struggle to observe these wavelengths because Earth's atmosphere absorbs infrared light. Water vapor in Earth's atmosphere, the same molecule being searched for in space, blocks the very wavelengths needed to detect it. High-altitude observatories and space telescopes can observe infrared, but 3I/Atlas has not been prioritized for such observations. The object is faint, its infrared emission weak, and telescope time is allocated to higher priority targets. Hydroxyl radicals produce emission at 18 centimeters wavelength, in the radio portion of the spectrum. This transition has been used for decades to study comets and molecular clouds. Proposals to observe 3I/Atlas with radio telescopes have been submitted, but none have been executed yet. Radio observations require long integration times to detect faint signals. The object moves against the sky background, requiring tracking adjustments, weather, equipment availability, and scheduling constraints have prevented observations from happening during the November brightening events. Only took a lack of available telescope time to leave major questions unanswered. Discovery favors the prepared, but also the lucky and the well-scheduled. Potassium emission at 766 nanometers remains marginal. Some spectra show a hint of enhancement at this wavelength, others do not. The emission is near the detection limit, making it uncertain whether the signal is real or instrumental noise. If real, it suggests potassium is being released along with sodium. Sodium and potassium are chemically similar, both alkali metals, and they often occur together in minerals. Their ratio provides information about the composition of the dust being released. In solar system materials, sodium typically outnumbers potassium by a factor of 10 to 20. If 3/8 shows a similar ratio, the potassium emission should be much weaker than sodium emission. Consistent with observations, if the ratio is different, if the object is enriched or depleted in potassium relative to solar system norms that would suggest compositional differences between the interstellar visitor and local materials, the data so far is too noisy to establish the ratio definitively. Carbon emissions are absent. No carbon monoxide, no cyanogen, no C2 or C3 bands that are common in cometary spectra. Either carbon-bearing volatiles are not being released in significant quantities, or they are present but at levels below detection thresholds. The absence is puzzling. Carbon monoxide is expected to sublimate readily at the temperatures 3/8 experiences. Its absence suggests either that CO is depleted in the object's composition, or that it is trapped in ice matrices and not easily released, or that it is present, but the observing techniques used are not sensitive enough to detect it. Nitrogen emissions are also absent. No molecular nitrogen, no ammonia, no cyanogen, despite cyanogen being one of the most easily detected molecules in comets. Nitrogen compounds require specific excitation mechanisms to produce visible emission. Ultraviolet light from the sun can excite some nitrogen species, but the efficiency is low. Radio observations would be more sensitive to nitrogen compounds, but as noted, radio observations have not been performed. Only took the absence of expected features to highlight how incomplete the observational picture remains. What is not seen is as important as what is seen, but absence of evidence is not always evidence of absence. The continuum spectrum, the smooth background light without discrete lines, carries information about dust. The way light intensity varies with wavelength reveals grain size distribution and composition. If dust grains are large compared to light wavelengths, the continuum is flat intensity does not change much with wavelength. If grains are small, the continuum slopes, with blue light scattered more efficiently than red light. 3I/Atlas's continuum shows a red slope. Intensity is higher at longer wavelengths than at shorter wavelengths. This is consistent with grains that are either very small, sub-micrometer, or composed of materials that preferentially absorb blue light. Organic compounds, complex carbon molecules are often red. Iron oxides are red. Amorphous carbon is greater red. The slope alone does not uniquely identify composition, but it constrains possibilities. Polarimetry adds another diagnostic. Light reflected from dust becomes partially polarized, with the degree of polarization depending on scattering angle, grain size, and composition. No polarimetric observations of 3I/8LAS have been published yet, but such observations are planned. Polarization measurements could distinguish between organic-rich dust and silicate-rich dust, narrow the grain size distribution, and constrain the coma's optical depth. Spectroscopy across a wide wavelength range would provide the most complete information. Observations spanning ultraviolet through near-infrared would cover emission and absorption features of all major volatile species, allow detailed modeling of dust properties, and enable measurements of isotopic ratios if spectral resolution is high enough. But such comprehensive spectroscopy requires space telescopes or specialized ground-based facilities, and neither has been available for extended observations of 3I/Atlas. Only took limited access to advanced instruments to make the study incremental rather than comprehensive. Science proceeds with the tools available, not the tools desired. The November 30th event arrives on schedule. Solar wind monitors at Earth detect the shock at 11:40 UTC. The coronal mass ejection follows 6 hours later. The magnetic cloud embedded in the ejection strong field strength reaches 90 nanotesla, the strongest yet observed in this cycle. The plasma density is high, the speed is sustained at 900 km per second, and the event duration is long. The magnetic cloud takes 16 hours to pass Earth. At 3I/Atlas, predicted arrival is November 30th evening. Observers around the world position their telescopes. The object rises above the horizon in South America at 2200 UTC. Telescopes in Chile and Argentina begin tracking. Initial brightness measurements show no change yet. The wait continues. By 2330 UTC, brightness has increased 10%. By midnight, 20%. The brightening is slower than previous events, rising more gradually. Spectroscopy shows sodium emission developing, weaker than expected for this stage of brightness increase. Oxygen emission is absent or below detection limits. The light curve is smooth, lacking the oscillations seen in some earlier events. By 0200 UTC on December 1st, brightness reaches 1.6 times baseline, then it stops rising. For hours, brightness remains nearly constant at this level, neither increasing further nor declining. The plateau extends through the night, observed continuously by telescopes in Chile as Earth rotates. Only took the strongest magnetic field yet to produce a brightening that is more subdued than weaker events. The relationship is not as simple as hoped. Anomalies are where understanding breaks down. The November 30th event should have produced the strongest brightening yet. The magnetic field was the strongest observed all cycle. The plasma density was high. The shock speed was comparable to the November 17th event. All indicators suggested a major response from 3I/Atlas. Instead, the brightness increase was modest, the peak lower than expected, the spectral emissions weaker. Several explanations compete. Perhaps the object is depleting its near-surface volatiles. 3 weeks of repeated outbursts have stripped material from active regions. What remains requires more energy to release, is buried deeper, or is bound more tightly in refractory matrices.